In this video, we're going to look at the local linearity or linear approximation for functions of three variables. And the idea here is that this is the analog of the tangent plane for functions with two variables. The idea is not as easy to imagine in a graphical way, but if we look at the math, we see the same kind of thing. What we have is a curved surface. Well, curved, I'll put in quotes here because it's not really a surface anymore, but it's some function that is not linear. And we could evaluate that at some point x, y, z that is near a reference point ABC. And what we get is, well, if you pick a point near ABC, the value is going to be close to the function value there. Again, think of it as temperature. The temperature at some point near a reference point is going to be pretty much the same, except we're going to correct for a change in x, and we're going to scale that by how our temperature changes as we move in the x direction, and we're also going to scale it by the step in y that we take and how quickly our temperature changes with y. Oh wait, that looks really familiar. In fact, that is exactly equal to the two-variable tangent plane or the two-variable linear approximation formula that we saw earlier. The only new element is the unsurprising inclusion of a third variable, because our function has three variables this time. We add in a change in z times the rate of change of our function with respect to z. Again, if you're trying to memorize these, there is just beautiful structure to it. It's the x slope times the difference in x's, y slope, difference in y's, and oh, there happens to be a z variable. All right, z rate of change times the change in z. In this example, we're asked to extend our idea of linear approximations to compute a fairly complicated expression here. Notice the powers here aren't 2, 2, and 2. This isn't a distance function. What we have are 2, 3, and 4, but we notice that there's a value of 6 here, which is, well, 6.02, which is close to 6, 2.96, which is close to 3, and 1.01, which is close to 1. And the idea behind this approximation, especially with the explicit instructions here of using local linearity around 631, is to imagine that this is really describing a function of x, y, and z that is equal to the square root of, well, some number near 6, let's call that x, and then we'll square it. Some number around 3 cubed, well, let's call that y, and some last number z to the power of 4. If that's our function, we can then use the linear approximation and say f of 6.02, 2.96, 1.01 is going to be approximately equal to our linearization formula at a nearby point. This is our a value, that's our b value, and that's our c value. So f at 631 plus the rate of change of x at 631 times, well, let's be clear here, this is our x now, this is our y, and this is our z. These are the points that are near the reference point, but different. And so we would take our delta x here, this is our x minus a form, and we repeat this pattern for all three variables. The y value is 2.96, and then we minus or subtract that from 3. And last but not least, we would take the z derivative evaluated at 6, 3, and 1, and use our 1.01 minus 1. Notice the ABC form here, x minus a, b, and c, 6, 3, 1 down here, and the three values that are close to the reference point. But the reference points are nice simple integers that will be easier to evaluate in this function. Now for reference, because we know we're going to have to compute derivatives, it's easier to compute those derivatives if we write everything as powers. So we're going to replace that square root with a 1/2 power. On the next page, we'll compute those partial derivatives. Here we have our function of x, y, and z written out as power. We can then evaluate the derivatives. If we have something to the 1/2 power, we get exactly the same expression to the -1/2. Subtract 1 from the power and bring the power down front. Oh, wait, we're not done. We also need to take the chain rule derivative of the inside with respect to x. So we'll have 2x's here. When we take the y derivative, going back to the original expression, we will have the same inside function to the -1/2 again, but this time we take the y partial derivative of the inside, 0, 0, and 3y squared. And last but not least, if we take the z derivative, we're going to go back to the original function. Don't get distracted by the earlier derivatives. Go back to the original function and take the derivative with the 1/2 out front, x squared plus y cubed plus z to the 4 to the -1/2 after the derivative. And then taking the z derivative of the inside, we're going to have 4z cubed. All right. Next up, we evaluate this at the point, and notice what we're trying to approximate again, but we don't use that point. We use the simple point 6, 3, and 1. At that point, I won't write in the 6, 3, 1 here in the interest of saving space, but at that point, the x derivative will be 1/2, 1 over the square root, 1 over because we have a negative exponent here, square root of x squared, that'll be 36, plus 3 cubed, that's 27, plus z to the 4, well that's just 1 to the 4, and then times 2 x's, and 2 times 6 is 12. Well, a quick side calculation, 36 and 27 and 1 is 28. That is exactly 64, and so that's the square root of 64, or 8. All right, so we have 1/2 times 12, that's 6, 6 over 8, or 3/4. Lovely. If we keep doing that same pattern, we're going to have 1/2, this whole expression here, the square root, well, we actually know what this is again, because it's the same x squared plus y cubed plus z to the 4, square root of 64, and then times 3y squared. 3 times 3 squared is 27, and so that would be 27 over 16 when we're done. And our third derivative is z derivative, 1 over square root of 64 for this expression, times 4, and z is just 1, so times 4. Tidying that up, we have 4 over 16, or 1/4. And we're actually missing one more ingredient. We actually haven't computed the function value itself. So f of 6, 3, and 1, that is going to be equal to the square root of x squared plus, wait, that's the square root of 64 again, by the time we plug in the 6 and the 3 and the 1, and so that is 8. Let's take a step back to the page before. If we want to approximate this complicated square root with various powers inside, what we're saying is it's basically going to be this value, which we just said was 8, plus all of these terms. So let's put that all together. F of 6.02, 2.96, and 1.01 is going to be approximately equal to 8 plus a slope of 3/4 times the x value we have, 6.02, minus the reference point we used for x, which was this 6. And we keep going. We have the next slope, 27 over 16, times the difference in y values, 2.96, minus the reference y value, which is 3. And notice again, these differences in the formula are all small. And plus the last term, the z slope, or the z rate of change, 1/4. There we have 1.01 as our new z, minus 1, which is our base point. And if we go through and calculate with all of that, we end up with a negative and a positive and a positive. By the time we work all that out, we get a number very close to 8. It's approximately 7.0 0.95. And so what we've done here is using only linear functions. There was no real significant calculation overhead in any of this work here. We're able to approximate, and if you compare the real value, it's quite close, this complicated combination of squares, cubes, and fourths of small, weird decimal numbers. We're able to get a nice approximation to that using this linear approximation approach. It's a very powerful technique in general.